Hello everyone, welcome to the first lecture of second week of our course. In today's lecture, we are going to talk about hyperspectral images and synthetic aperture radar images. Previously, in the first week, we have introduced Earth observation. We have talked about different acquisition platforms. We have also talked about some example Earth observation talks, which we keep visiting from time to time, and we'll revisit again today as well. We have talked about multispectral images, and there we talked about Sentinel-2 images, whereas in today's lecture we'll talk about Sentinel-1 image. So in the last lecture itself, we had already started talking about hyperspectral images. In this lecture, we will continue that discussion. So as we have already briefly discussed in the last lecture, hyperspectral images are very useful for material identification. Spectral signatures act as material fingerprints. However, similar classes, of course, may have overlapping signatures. The classification relies heavily on the spectral separability, and thereby we will later discuss when we talk about hyperspectral image analysis in one of the coming weeks. We'll discuss in addition to the spectral separability, like how taking the spatial context into account and thus moving from 1D convolution to 2D convolution to 3D convolution helps. So with this rich spectral information in hyperspectral images, what we also see is spectral redundancy. Adjacent spectral bands are often highly correlated, and this redundant information may increase computational cost. Here, it's important to emphasize that adjacency is also in the terms of application. So there might be specific application where a group of bands, they like the separability provided by those bands, that's redundant. Whereas there might be other application where probably the separability provided by those bands, they are still useful. However, in most application, dimensionality reduction becomes important, and feature selection or extraction often improves efficiency. So this feature selection or extraction, this we will be talking about a bit more soon. One of the important hyperspectral image analysis task is anomaly detection. So as you would have remembered that when we discussed multispectral images, we said like some of the important talks related to the multispectral images included classification, semantic segmentation, change detection. So those talks, of course, they are also still relevant in the case of hyperspectral images. But these are some other tasks which are often like we encounter in the context of hyperspectral images. It's not that anomaly detection, I mean, cannot be a problem statement in the context of multispectral images. However, it's more relevant when we talk about hyperspectral images. So anomaly detection here identifies the spectrally rare targets, and the assumption is that no prior target signature is available or is to be used. If there is prior target signature available, then it rather becomes target identification task. Anomalies differ significantly from the surrounding background. I mean, that's what making it anomaly, right? Like if it was very similar to the surrounding background, then I mean, it would have become part of the background itself. And thus, this is very important in surveillance and also environmental monitoring. So, like think about like some material deposition, even in otherwise like city or somewhere where like those material deposition is otherwise rare. This could have even like some security implications. So yeah, I mean that's what hyperspectral anomaly detection is, that to capture these subtle spectral deviations and detect such small or even camouflaged objects from the spectral signature. So this is one important aspect. I mean, such objects can be quite small in size, and we should still be able to detect them. So later, I mean, again, like when we will talk about hyperspectral image analysis in more details, we will see like the hyperspectral anomaly detection data set. There, the number of anomalous pixels, I'm talking about like the standard data sets used in academic research. The number of anomalous pixels are very few. So I don't remember exactly right now, but if my memory is good, like there is one data set where probably, or rather like one image scene, I mean, where there is just 21 pixels, I think, which is anomalous. So yeah, I mean, that's what we're talking, that okay, like we need to be able to detect such small anomalies. The applications of hyperspectral anomaly detection include defense, surveillance, let's say oil spill detection, mineral exploration, urban monitoring as well. So with this, let us again emphasize on the differences between target detection versus anomaly detection. In the case of target detection, the usual assumption is that we are working with a known target signature and we are trying to match this target signature to our given ROI. Whereas the anomaly detection assumes unknown targets. Thus, it focuses, so we're talking more in the context of hyperspectral anomaly detection, it focuses on the spectral rarity. So the assumption is that, okay, like whatever like spectral signatures are present in the background, if we can capture those distributions, and then like now whatever is not otherwise present in the distribution, we can call that as anomaly. And yeah, I mean, this of course is much challenging than supervised target detection task, where you are working with known target signatures, versus here that you are working with like you are trying to find out a signature which you don't have like a exact idea. And in such problem, one important aspect to remember is that often it's important to tune the false alarm rate. High false alarm will reduce reliability. However, also you probably not want to miss the anomalies, right? So often the algorithms are designed in a way that you'd rather go for detection of like all the anomalies and plus some false alarms, and then you will on the top of this use some kind of post processing to reduce the false alarms. The post processing can be as simple as like using some known land cover map. Like let's say you have the land cover map and you let's say like know okay from the land cover map that these are the pixels covered by water, and the anomaly that we're looking for that's not in the water. Okay, but let's say water is like somehow susceptible to trigger false alarm. So with this known land cover map, you can now remove those pixels which were those water pixels which were detected as anomaly. Another important aspect which I briefly mentioned already in hyperspectral image analysis is dimensionality reduction. So recall that it's not that with the multispectral images, like even with the Sentinel-2, we are not doing any kind of dimensionality reduction. We say that even with Sentinel-2, sometimes depending on the specific application that we're interested in, we actually like let's say choose a particular number of bands. Like let's say we are interested in urban applications where let's say we are let's say depending on the exact application again, because urban is still like a broad category. So depending on the application, let's say we are sure that okay like RGB and NIR, those 10-meter bands are the only ones which are useful. So in that case, what would we have done? We would have like just used those 4 bands, right? Then we said that also depending on so this the first class that I just mentioned is picture selection or band selection. Whereas the other categories also like sometimes depending on the application, what we would have done is that let's say we would have converted the bands into like let's say we would have just taken normalized difference vegetation index, normalized difference built up index. Okay, so this is what we are primarily interested in. So this in a way is a feature transformation. And what we see in the case of the hyperspectral dimensionality reduction is the same pattern. We are interested again in feature reduction or feature extraction or transformation. So, I mean, we have already discussed like how dimensionality, if like let's say we are really not using those fine-grained discriminability in those bands and all, that the dimensionality actually hurts. So the benefits of dimensionality reduction includes reduction in spectral redundancy, thus improvement in computational efficiency, may enhance classification performance as well. So again, I'm making it clear that whether it will improve the classification performance or not really depends on the application. We just end up like like dropping band like that, then what's the even purpose of having hyperspectral images, right? Another aspect is also like a visualization and interpretation, which becomes much more easier, much more convenient with less number of bands. So one aspect is the spectral correlation, which we have already discussed, that neighboring spectral bands are highly correlated. So which means what? That we may probably just drop some of the bands for many applications, and still like we have all the needed information and that we wanted. And this basically leads us to the feature or band selection. In this case, it's probably better to call as band selection. The other possibility is the feature extraction. So what's happening is that in the case of feature selection, we are choosing the important original bands, whereas in the case of feature extraction, or you can also call it transformation, we are creating a new transformed features. The selection thus preserves physical interpretability. So the bands that you are having, they're still the original bands, right? A subset of them. Extraction often achieves stronger compactness, but in some way, like you're losing physical interpretability, because what you are obtaining often depends again on like, okay, like what is the transformation that you are applying. Like the example that I gave before for Sentinel-2 images, like let's say we are converting the given bands to normalized difference vegetation index, normalized difference built-up index. Probably in those cases, this complaint is not so much true that we are losing interpretability. We know very well what vegetation index or built-up index is. However, there are other ways which we'll discuss later of extraction, which actually like we will lose the interpretability. So the feature selection selects informative spectral bands or removes redundant or noisy bands, thus preserves original physical meaning and useful for interpretable analysis. One possibility there is doing some kind of band ranking. Okay. The other is the feature extraction. It transforms data into compact representations. New features combine information across bands. It often improves separability and often widely used, like when we are trying to do classification. It's the feature extraction used in tandem with this. Another important problem statement that we deal in hyperspectral images is a hyperspectral unmixing. So what happens is that the hyperspectral pixels, they often contain mixture of material, and this is again depending on like the spatial resolution. So I mean, this would not be so true if we are still talking about hyperspectral images, but the spatial resolution is quite high resolution. So with the unmixing, what we aim to do is to decompose these pixels into constituent materials. The constituent spectra, we call them as end members, and then we are like denoting the proportions denoted by the abundance. Another important aspect in the hyperspectral image analysis is enhancement. So enhancement is aimed towards improving quality and usability of hyperspectral data. It includes denoising, super resolution, inpainting. So some of these problems are also very much relevant in the context of multispectral images as well, like super resolution. Often we try to, like since Sentinel-2, this comes as 10 meter per pixel. Often there are research works which try to actually upsample Sentinel-2 to a higher resolution. Like let's say one possibility is that, okay, you take Sentinel-2, you take let's say planet images of 3 meter per pixel and you try to train a network, then like somehow this transcodes the Sentinel-2 10 meter to 3 meter per pixel resolution. So once this training has been done, then later like when you have actually deployed your system for whichever task that you're using it for, you can now always super resolve the Sentinel-2 images. And these kind of methods, of course, has its limitation. Otherwise, we would have always like used super resolution as a compulsory pre-processing step, but that's not the case. In painting, of course, is also important aspect. So we'll be discussing these aspects in details later when we talk about hyperspectral image analysis in one of the subsequent weeks. However, we will talk a bit, like just a minute or so, about especially about the denoising aspect. And interestingly, in the case of the hyperspectral images, the noise characteristics may vary across the bands. The denoising in the hyperspectral images, this is aimed to remove the unwanted signal perturbation while preserving spectral fidelity. So think about this. One very simple approach can be spatial filtering, like just to process spatial neighborhood. Let's say we are using min filter. This is a simple approach, but this can may blur details. And on the top of that, the issue is that, okay, we are talking this in the context of hyperspectral images, right? Not in the context of like single band or multispectral images. So such spatial approach, what this may do is this may like at the same time like blur the details, spatial details, and also it has limited spectral modeling capability, which we would argue that is important in the context of hyperspectral images, right? So maybe we want to somehow also incorporate some spectral context in the filtering process, or like the deep learning based methods that we would be talking about. So with this, let us move to SAR. We will take forward our discussion of the hyperspectral images, the tasks that we have mentioned in the last 20 minutes or so in one of the subsequent weeks in more details. Now let us introduce SAR, synthetic aperture radar, another very important class of sensors used in Earth observation. In fact, there are so many works which combines Sentinel-2 and Sentinel-1, Sentinel-2 multispectral, and Sentinel-1 SAR image. So, first of all, let's say very briefly, try to understand why this name synthetic. So what happens with this is that the longer the antenna, the better is generally the resolution achieved. However, of course, I mean, you cannot just have longer antenna just like that. There are physical constraints. So what one can do is you can simulate a long antenna by taking advantage of movement and combining data collected using a shorter antenna. So for this process, I mean, this name has come synthetic. It's very important to understand the differences of the SAR with respect to the optical images. Optical sensors, this depend on the, since this is passive sensor, and this depend on the sunlight availability, and it's also get impacted by cloud. Whereas on the other hand, SAR is an active sensor. It transmits its own microwave signal, so it's not dependent on the ambient light, and thus it can acquire images during both day and night. And on the top of these, microwaves can penetrate clouds. So we have discussed before, right, like what can happen with the Sentinel-2, that you had like right now an earthquake or something, and you want to like quick change detection map. However, what can happen is that there are cloud and you could not really get usable acquisition. This would not be the case with SAR. So SAR is an active remote sensing system that sends microwave pulses toward the Earth's surface. Objects reflect part of the energy back to the sensor, and each pixel then represents radar backscatter rather than reflected sunlight. So, another important aspect to keep in mind in the case of SAR is that it uses a side-looking geometry. SAR observes the Earth from the side rather than directly below. And what happens is that geometry strongly influences object appearance in SAR images. To understand the backscatters a bit better, what happens is that the smooth surfaces, if we are talking about, let's say, column water, this reflect energy away from the sensor, much like what you would imagine in the case of mirror, and thus they often appear dark. So for this reason, I mean, like if you're trying to detect such calm water, often SAR is a good choice. Whereas on the other hand, the rough surfaces scatter energy in many directions and often appear comparatively brighter. On the other hand, what happens with the vertical urban structures is that they typically reflect signals off the ground and back and appear bright. With the SAR images, we see several significant and interesting geometric distortions such as layover, foreshortening, shadow. So we'll not go into the discussions of all this, but if you're interested, you can look up some remote sensing specific course. And like if you are like really like interested in working very much into the SAR, understanding these aspects is also very important. One important aspect, also pretty much from the computational aspect, is also the presence of the speckle noise in the SAR images. Speckle is not additive noise, it's rather multiplicative noise. And for this, often filtering methods, I mean, at very simple level, like let's say median filtering, there are other like more specialist filters, they need to be applied before further, feeding the SAR image to our image processing pipeline. So why is SAR relevant in Earth observation? Because it works in cloudy and nighttime conditions. It is sensitive to surface roughness, moisture. It can penetrate through vegetation canopies. Okay, so depending on the band, so let's say like not so much if we talk about X band, not even for C band, but there are other bands which like we'll see soon, where like we see significant penetration, and that is one very important aspect of using SAR. So we took this example before, right? Like destroyed buildings, partially destroyed buildings, and in this case, the SAR, we said that optical images has limited capability. However, SAR, they have quite good capability in such cases. So talking about the SAR bands a bit, we have X band, which provides high resolution images and is very useful for urban mapping. We also have C band, which is often used for land cover mapping, flood mapping, agriculture. S band again used for land cover mapping, agriculture. L-band to understand forest structure, biomass estimation. So by now you would have guessed, right, like which of these bands shows good penetration. And P-band provides even better vegetation penetration, and often also used in subsurface studies. Another important aspect is also polarization. So what happens is that since radar waves, we're talking about electromagnetic waves, they can be transmitted and received with different polarizations. And this leads to the possibilities of different polarization channels like HH, VV, HB, VH. So X-band, what we see is that like most of them are actually commercial. TerraSAR X is one example, Cosmos SkyMed is one example of X-band SAR image. Whereas C-band, I mean, I've talked about already Sentinel-1, or like at least mentioned side by side to the Sentinel-2 a few times. Sentinel-1 is C-band SAR mission operated by the European Space Agency as part of the Copernicus program. So you have already heard about this Copernicus program also, right? And depending on the availability of the different Sentinel-1 satellites, the revisit intervals have varied over the time between approximately 6 to 12 days. So there is an interesting history. You can read a bit about this on your own. Like at some point there were two of them, then one of them went down, then another was launched, and so on. Sentinel-1 data we find in formats such as single look complex, backscatter and phase information, also ground range detected GRD, which doesn't provide phase information. So often, like when we're working with this data, like we'll see like, okay, these additional formats and all this information are provided along with this. Similarly, in the case of Sentinel-1, we also have acquisition modes such as IW, which has 250 kilometers worth resolutions of 5 cross 20 meter. So you see like how the resolution, that's another important aspect here, like how the resolution may vary along the different spatial direction. There is also strip map mode. Another important SAR sensor that deserves mention is NISAR. So NISAR, this is a joint mission conducted by ISRO and NASA. This is a very recent one. It carries, interestingly, both L-band and S-band SAR systems. Okay, so with this we'll stop here. We also have a week dedicated to SAR image analysis later in the course, where we'll discuss more about all these aspects. Thank you.